Hello again. Now to pick up where we ended the previous video, we will first talk about the distributed E architecture. Distributed E architecture means sometimes more than one ECU can be used for one application. For example, for ADAS maybe two ECUs, for communication more than two ECUs. So for every application there are several ECUs which are distributed along the length and breadth of the vehicle. Okay. Now in a distributed architecture, electronic control units are distributed throughout the vehicle and each responsible for specific function or subsystems. Okay, this word is extremely important. Distributed, distributed throughout the vehicle. Now, communication between these ECUs occurs as a throughout a network such as CAN. Okay, not specific CAN I just as an example, it can be LIN or FlexRay or MOST or Ethernet, it can be through any kind of communication protocol, but CAN is definitely by far the most popular kind of protocol. Now a distributed EEA features a number of ECUs dedicated to specific tasks, cumbersome wiring and high system weight. Now this is something I briefly touched upon in the previous video, saying I told you that this distributed electronic and electrical architecture, this is the acronym for it, EEA, features high number of ECUs, and because of the entire distribution along the car, very cumbersome and complex wiring, and it also leads to high system weight. Now in the modern vehicles, wiring can account as much as 20% of total EEA cost. Now because of the weight and the length of the wiring, this can almost account for 20% of the total architecture. Now the wiring harness is the third heaviest component in the vehicle. This is something which I have mentioned in the previous video, and I am re-emphasizing it because this is extremely important. So tomorrow when you work in the architecture, this is some important parameter which you need to keep in mind while designing the wiring harness. Now the advantages of distributing the EEA or modularity or redundancy for critical functions. Okay, so there are some advantages. It's not that distributed is totally bad. So there are some advantages, like it is very modular and redundancy for critical functions. So in this case, failure of one area does not necessarily affect the entire system. So the failure will remain isolated in a silo. It won't affect the other system. Another key advantage derived as a result shifting towards is reduction in the wiring requirements, thereby cutting the vehicle cost. Now this is the advantage which all the automakers are chasing: reduction in the wiring requirements, therefore cutting the vehicle cost. However, distributed EEA is limited in scalability, and this is the main disadvantage. It is limited in scalability. It suffers from complex wiring issues due to multiple ECUs and plagued by limited bandwidth. As an example, from an ADAS perspective, in a distributed EEA, adaptive cruise control and front collision warnings should have separate ECUs. So you can understand, now as ADAS features are increasing, in a distributed perspective, just two features or two functionalities will have two different ECUs. So suppose if there are some 10 ADAS functionalities, then it will have 10 ECUs. So you can understand how much the wiring is becoming complex, and also how much extra weight it is adding to the vehicle. So naturally, it is common sense to understand, as the weight of the vehicle is increasing, fuel efficiency will be badly affected. All right. So let's see the next type of architecture. So next, from distributed, the next step or the next positive growth happened in the form of domain EE architecture. Now this architecture is a hybrid approach that combines the aspects of both distributed and centralized architectures. Now it organizes ECUs into domains based on their functions. For example, powertrain, chassis, ADAS, infotainment. Now each domain has its own controller which manages the functions with that domain. Okay, now each domain understand this very carefully. Each domain has its own controller or ECU. So for everything, powertrain there is separate ECU, chassis has separate ECU, and ADAS also has separate ECU. Especially in ADAS, all the functionalities are integrated or clubbed into one particular ECU. That is the biggest advantage. Now the domain architecture can be viewed from the lens of data domain or logic domain in certain functions or group. For example, infotainment, chassis, body lights, cabin, driver monitoring systems would which have dedicated functional controllers, aka domain controllers, aka ECU. Now the architecture advantages such as improved organization, system modularity and enhanced communication efficiency within specific domains. Okay, and even though this architecture reduces the number of ECUs and wiring requirements, the reduction tends to be small. Understand this carefully. Now, even though it is reducing, certainly there is an advantage, it is reducing, but somehow this did not yield the reduction as intended or as much as intended. There was reduction, but it was just a small. For example, the chassis control still must have wires connected to the four wheels of traction control. Okay, so this was certainly an improvement, but it does not exactly improve the wiring harness or the reduction in the weight as much as expected. So automakers went for further improvement, and they came onto the zonal E architecture. Okay, these pictures understand very carefully this domain architecture and centralized architecture. You will clearly understand what's the difference between domain, centralized and zone architecture. Now, this architecture must be viewed through physical domain. So, in a physical perspective, in the zonal architecture, the vehicle is divided into physical zones such as rear right, rear left, center, front right and front left. Now, all functions within that zone are handled by one computing power. For example, it may be infotainment. Infotainment is suppose on the left front of the vehicle. If it's right hand drive, right hand side will be steering and left side will be the infotainment. So, in the left side, the entire infotainment will be handled by the concerned ECU, so that the ECU is very near to the infotainment. This is the concept also of edge computing, where the end application is very near to the ECU. Now, some key benefits of the zonal architecture are reduced wiring requirements and improved communication, data transfer and over-the-air updates, faster software development and reduced costs and weight. So, this definitely showed a drastic improvement when compared to domain E architecture. Zonal E architecture definitely showed a drastic improvement, and however, the latency and security are key challenges when implementing this architecture. Latency and key security also have definitely improved, but they still are definitely key challenges which need to be addressed. Okay, I recommend all of you to pause the video and see this clearly, these drawings. You will clearly get an idea what exactly this zonal E architecture means and how or why it is so advantageous. Now, let's see one Bosch centralized architecture. Now, what is this centralized architecture? This is even more advanced than zonal architecture, and Bosch is developing this new electrical and electronic architecture that ensures complexity of future vehicle system stays manageable. Okay, so as you can understand by now, because of this diversified location or positioning of the ECUs, there is a huge complexity, and this complexity must be drastically reduced. Okay, and at the center of this development is a shift away from today's domain specific E architecture towards a cross domain centralized E architecture that uses only a very few powerful computers instead of great many individual control units. So, this centralized architecture aims at reducing the number of ECUs by replacing the ECUs with high performance computers. Alright, and these vehicle computers will be connected to the remaining embedded control units as well as sensors and actuators via zone ECUs, and Bosch calls this approach as vehicle centralized zone oriented E architecture. The reduced number of control units. Now, this sentence is extremely important. The reduced number, this has definitely reduced the number of control units, leads to lower system complexity coupled with simultaneous increase in the security. Okay, this security is actually a double-edged knife because it is definitely reducing the number of entry points or attack points. But once a hacker successfully enters a particular ECU, he will have access to all the functionalities. So, as long as nobody can hack, this centralized architecture is definitely safer than distributed architecture. But by mistake, if somebody successfully attacks, then he has access to all the functionalities. So, this is like a double-edged knife, double-edged sword, where it has both advantages and disadvantages. Alright, and now this led to a tangible amount, that is 20% fewer embedded controls and today's EE architectures consist of 100 control units or more. All right, and it also led to 10% lower cost through material and software savings. 10% is a big amount, especially luxury automobile. 10% can drastically reduce the cost. All right. Now, what are the overall challenges of these zonal EE architectures? Now, the main challenge is the conspicuous product and system requirements. Okay, these system requirements are missing solutions in the standards. As of now, there are no standards in the safety requirements of the zonal EE architecture. And there is a huge problem of electromagnetic compatibility introduced by combination of data and power distribution. Now, coming to the additional space requirements for installation in the vehicle, the heat dissipation on the high performance computing units or power switching and early startup scenarios. Now, these are all the various types of challenges. Okay, so when a high performance computing is happening, naturally processing is very rapid and that may lead to heat dissipation. And when it comes to implications on the system architecture, partition of the data processing, smart sensor versus cloud processing. This is a very important implication. Partition of the data processing. Okay, so sometimes data may get processed with the sensor, and sometimes the data may get processed in the cloud. So this advantage has to be weighed or compared with each other. Integration of high data rate sensor actuator such as high data rate cameras, example 1 Gbit per second. Now coming to the integration of low complexity and legacy devices, example cheap ECUs, LIN and CAN. LIN and CAN are basically meant for cheap ECUs because high performance computers, they are basically using automotive protocols like Ethernet or T1000BS. Now coming to the interplay between the multiple real-time communication channels, legacy traffic and class traffic. All right, so where there is so much of data, naturally there is a data traffic and this interplay must be managed properly. Okay, this is one important implication of the system architecture. Now coming to the structural architecture, optimization of various cost trade-offs such as production, material and labor. So when it comes to production, this has to be clearly addressed. So production versus material versus labor. So are we reducing the labor? Are we reducing the production cost? Are we reducing the labor cost or man hours? All these things need to be clearly undertaken in the business perspective. Now when it comes to organizational barriers between communication network versus production distribution, departments on the OEM supplier side. So these are the various organization barrier. In an OEM network, people may have some demands and power distribution may have another demands. All right. So this will this is also an important organization barrier as far as the OEM is concerned. Now when it comes to collaboration model in the development and production in between OEM, tier 1 and tier 2, now this is the biggest challenge as far as the supply chain is concerned. So when you develop the entire architecture, the ECU can be generated or produced by one company, wiring harness can be produced by another company, the communication protocol can be configured by another company, the stack can be produced by another company. So this entire calibration model and how this collaboration is being directed towards the zonal architecture, that remains a big challenge. And availability of cutting edge ECU components, example TSN enabled switches and eFuses. And last but not the least, the global deployment of the uniformed zonal gateways at OEM production sites in dedicated car lines and trim levels. So exactly when in the assembly line, when the car is manufactured, this deployment of the uniform zonal gateways, every zone has a uniform gateway and this should be deployed in the OEM production site. This is a challenge that is being posed in front of many OEMs. Now, advantages of the zonal architecture. What are the main advantages? As a vague thumb rule, we can reduce the wire length from 15 meters to 5 meters. So naturally, proportionally, the complexity will reduce. And it also uses lower cable quality as we need lesser ego cancellation. Okay, because the vehicle wire length is coming down, echo cancellation need also comes down, and therefore we don't require an expensive quality cable. Even a lower quality cable can be used. It also optimizes equalization and echo cancellation circuits, uses lower baud rate and higher order modulation. It increases the power and area savings, and this is important. It reduces the power used, and it reduces the need for hardware parallelisms. Again, this also translates into area savings. Okay, I request all of you to go through this particular small flow chart. You will clearly understand we, uh, as the architecture is evolving, in how many advantages are being enjoyed by the OEMs. Thank you.